On behalf of the Statistical Society of Australia, I welcome you to today's webinar. It's to be given by Daniel Elazar. He's well known to many of us, but for those who may not know him or may not be in Australia, indeed, Daniel works in the Bureau of Statistics. He's a director in the data linking methods section and has been there for a while. He's a very experienced officer, and we look forward to his presentation today. In the spirit of reconciliation, the Statistical Society of Australia acknowledges the traditional custodians of country throughout Australia and their connections to land, sea and community. We pay our respects to their elders, past and present, and extend that respect to all Aboriginal and Torres Strait Islander peoples who have joined us. I'll pass over to Daniel. I'm sure that Daniel will take some questions at the end. If you wouldn't mind placing them on the chat, and I'll filter them through to Daniel at the end, or you can put them through at any time during the talk, but we'll reserve the questions till the end. Daniel.
Thank you, Stephen. Thank you, Mark. It's a pleasure to give this webinar, and I thank the Stats Society for asking me and for Anders for giving me the opportunity. So this is actually a sequel to a webinar given back on the 17th of August by Anders Holmbe and Rajiv Simaraj on can multiple disparate data sources complement each other. So what I'm going to primarily talk about is the methods that we use in the ABS, some of our challenges, and I'll talk about that throughout the talk. Next slide, please, Mark. Thank you. So what I'd like people to get out of this talk, firstly, is we're going to talk mainly about the data linking methodologies that we use here in the ABS. I'm going to talk about the methods themselves. Importantly, the ABS person linkage spine, which is kind of like the centerpiece of the way we productionize linkages, large-scale linkages, using many administrative data sources. Those data sources that we utilize that go into the spine. Also going to talk about current and future research and how we quality assure not only our data sources, but the spine itself and our methods. Next slide, please. So just a bit of history. So the ABS has been engaged in data linking methods since the very early 2000s. So there was kind of like a 10-year period of development work, carrying out a whole lot of empirical studies to see what methods work best. I guess Australia is a little or somewhat more unique or different to the Northern European countries that have registers with personal identification numbers, where the linkage is quite straightforward. We in Australia and a few other countries, we need to rely on linking on certain personal attributes such as name and address and age and sex, country of birth, things like that. Their name and address are certainly in an encrypted or encoded form, so people doing the linking don't actually get to see that personal information. So anyway, the quality studies basically came to a head with the 2006 census, where we sort of looked at different methods and quality assured the linkages that we did. We could do that because we could compare them with the actual using name and address information as the gold standard, and see what sort of compromises and what compromising quality there would arise. I was also utilizing the automated post enumeration survey, which is a survey that is linked to the census in order to estimate under coverage and over coverage for that matter. It's an important survey. It goes in hand with the census to produce the demography, estimated resident population counts. The ABS gained accreditation as a data integrating authority in 2012. And 2017, importantly, the ABS and a number of other government agencies got funding from the Australian government for the establishment of the Data Integration Partnerships for Australia. So that provided funding for a 3-year period, which only ended in June 30 this year. And that was important because it really sort of, it was really injected a lot of money into establishing systems and methodologies and producing a number of important linked data products that government agencies, policy researchers, and researchers in academia have been able to utilise. And 2018, 19 and 20 saw the production of 3 versions of our ABS person linkage spine, which I'm going to cover shortly. Next slide, please, Mark. Okay, so what are some of the challenges of large-scale data integration? So we have a number of different data sources, mostly administrative at the current time point, but we'd like to extend that certainly to non-conventional data sources such as energy use or whatever into the future. And we also have a series of methods that we use to integrate that data, and we obviously importantly have users who need to utilize that data to get a better understanding of the social, economic and well-being of Australia. And some of the objectives, the goals that we really have are to provide an enduring assets of linked data sets that can be used as longitudinal linked data sets for researchers to use. Users obviously want high quality linkage, and they also want so a linkage in terms of the quality of the data sets being linked, the methodologies used to produce the best linked data set, but also the analysis of that data set, it needs to be of high quality as well. And that's a bit of a gap at the moment. There's been a fair bit of academic research into developing methods for taking into account the linking uncertainty when analysing linked data, but it's something that I'll talk about later that we hope to fill that gap in the next couple of years. Obviously, efficient production of linked data sets, flexibility in linking different types of data sets, including admin and unconventional sources I just mentioned, such as all sorts of data like energy use, locations data and the like, and also importantly, doing all these linkage exercises while still ensuring the privacy and security of the personal information that is held there. Next slide. So I'm just going to go back to basics in terms of like a standard framework for linking data. I know a lot of you are going to be very familiar with precision recall in terms of the machine learning area. I'm just going to go over it just for clarity and also to point out some just slight nuances when we're using this framework for data linkage. So in data linking terminology, we use the term matches to refer to the true links, where 2 records on 2 different data sets being linked refer to the same entity, the same person, the same business or the like, and that's the truth. That's the real agreement between those records that they do belong to the same person. Now that's something that we don't always know in truth, and that's the whole goal. That's why it's data linking is a statistical problem. There are uncertainties, and it all comes down to how we deal with those uncertainties. And similarly, we have non-matches, 2 records on 2 different data sets we're linking that do not refer to the same person, the same entity. And the goal of data linking is to try and link those people, those records that do belong to the same entity. So when we do our linkage exercise, however we choose to do that, we're effectively making decisions about which record pairs are matches, or we call them our links, but ideally we want them to refer to true matches in the population. So the black line there is the linkage decisions that we make, and when we link a whole bunch of record pairs on 2 data sets, the blue stars there represent or the stars, I should say, represent the matches, and the non-matches are represented by triangles. The blue and red refer to the correctness of the decision that we made in carrying out that linkage. So we hopefully get majority right. The links we make do refer to true matches. There might be some that we miss, and we call them false negatives. And likewise, we might pick up in our linkage some record pairs that are actually non-matches, and they're indicated by the red triangles. And we also make the correct decision in not linking a whole bunch of non-matches, and they're referred to as true negatives. And two measures that are used in data linking and machine learning and many other areas are precision and recall. So precision refers to the true positives, the ones we get right in our linkage decision, divided by the true positives plus the false positives. Now that denominator there is basically just the number of links. So, and similarly, recall is the true positives now divided by the true positives plus the false negatives. And that denominator there is actually the matches. So you can think of the precision as the proportion of links that we make that are true, that are matches, and likewise recall is the proportion of matches that we did choose to link. Okay, next slide, please. So there's two extreme things we can do when making some linking decisions. First of all, we could be ultra conservative and just link one record. I forgot to point out that just in this schematic diagram here, the matches over to the far left are of better quality. There's much we're much more easy. It's much easier to discriminate between them and identify them as matches, so that would correspond to the fact that they agree on all the linkage variables that we use, and also that there's pretty much no competing other links, so that they're fairly unique. And as we get closer to the border between matches and non-matches, that discriminative power becomes less. Similarly for the non-matches, the ones that are very obviously non-matches because they don't agree on any of the linkage variables are over there to the right. So the most conservative thing we can do is just pick the most definite certain link that we can make and just link that. And obviously that's not going to be an ideal decision. It gives 100% precision because everything that we did link was a match, but obviously we only linked one, and the price we pay, of course, is that recall will be quite small because there's all those red stars there, all those true matches that we failed to link. Next slide, please, Mark. The other extreme thing we can do is to link absolutely everything, and that makes our recall look a whole lot better. We would get 100% recall, but of course now we have the issue that we've got a whole lot of false matches, false positives that we've included in our links, and so precision now falls lower. Next slide, please. So of course the ideal thing that we want to do is just to link the true positives and exclude the non-matches from our linkages, and of course that will give us 100% precision and recall at the same time. And so this is where the linkage strategy comes into play. We need to have the right way of making a decision to link just those matches. That's not always possible. There's always going to be some degree of error, but that is our goal. I should also say there's another way of thinking and looking about this in this framework in terms of data linking, which I'll describe at the very end of this talk. I'll discuss that then. All right, next slide, please. Okay, so precision versus recall. What we tend to do is as we increase the number of links, we could, if we knew we could calculate precision and recall exactly, then we would get plots similar to this. So precision starts off at 100%. We have 0 false positives because we're only picking the very best link candidates to link, but of course our false negatives can start to increase, and then it sort of approaches a cliff where it starts to go down as we start to include more false positives in our linkage exercise. And similarly, recall does the opposite. Basically, it starts to climb up, and of course the challenge here is to try and pick the best trade-off between precision and recall. I must say that for most good quality linkage, decent quality linkage exercises where you've got good linking variables, you've got relation and the like, then that overlap between that crossover between precision and recall pretty much occurs, is fairly easy to define, and it also occurs pretty much where precision starts to drop off. So basically, recall doesn't generally, or very rarely, if extremely rarely, does it reach 1 before precision starts to drop off. Because if recall does reach 1 earlier, well then you've already linked all your matches, and if you keep going, you're going to just start to include more and more false positives, so your precision starts to drop off. And this is why in the ABS we tend to focus more on precision. I know it's been commented before that, well, why don't we calculate recall? And I'll talk about how in the following slides how we can calculate recall, but there are some other statistical issues that impact that. The probably importantly, as you saw from, or you see from the formula here for recall, is that the denominator of recall requires you to know the true match population, and that is the real issue. Sometimes that's easy, like when you know that that one of the two data sets being linked is definitely a subpopulation of the other data set. So for example, social services and Medicare, pretty confident that just about everyone receiving a social services benefit is going to be on Medicare. There might be a few exceptions, but it's largely true. We do get into, it becomes harder when you've got two populations that are where you're not really 100% sure of the true overlap, and hence recall is much harder I should say, to estimate. An example of that is say for example the social services data and personal income tax data, where it's harder to say like how many people receiving a benefit also lodge a tax return. There might be information on that in the social services data, but I'm not sure we actually obtain that or acquire that information. But there are other things we can do. We could use surveys that we use to try and estimate where those two pieces of information. So, for example, income and social benefits are reported, such as the survey of household income, and we could use that as an estimator. But of course, that does suffer from some reporting errors. For example, some people might think they're entitled to a benefit but are not actually receiving one, or they've applied for a benefit. And there's also the issue of responding. Sometimes, well, often it's only one person in the household responds on behalf of the other members of the household, and they may not be fully aware of whether a person's actually receiving a benefit. Okay, next slide, please, Mark. Okay, so as an overview, so our two methods that we use in data linking are deterministic linking, which is really a whole sequence of deterministic linkages, and probabilistic linkage. Now, deterministic linking requires agreement on all the linkage variables. It either agrees or doesn't agree. Probabilistic is a bit of a different approach. So I'll just go through deterministic first. So first of all, there's our linkage variable. So we design a whole sequence of different combinations of the linking variables. So we might have linking variables that are like, for example, name and address, age and sex, date of birth, country of birth, a whole lot of other indicators. And we take all sorts of different combinations of those variables and they become a linkage key in the computing sense. So we basically can very quickly sort or order those keys and just choose the ones that do agree. So it's basically, the advantages are that it's a fairly simple, relatively simple approach. It's pretty fast. We can run a linkage using our deterministic methods pretty rapidly on very large data sets. We can incorporate fuzzy linking by, for example, we can accommodate age being out by 1 or 2 years or the like. And with statuses, so what is a status? Statuses are basically all the changes, excuse me, in name and address and similar linking variables over time. So the advantage of getting continuous administrative data is that we have a history of previous names, previous addresses, previous qualifications and the like that we can incorporate into our deterministic linking program, and that has been done. And that actually is very, very important. It gives us a lot of power in picking up people who have moved and really improves the quality of our linkage. The other important thing is that there's no blocking. Often blocking, like in probabilistic linking, is used to reduce the search space. So you're only linking within a mesh block or a statistical area 1 and doing the search for possible links within that geography, say, which reduces the time it takes but the problem, the potential problem, is there could be a true match that is outside that particular block. Probabilistic linking, on the other hand, is based, it's based basically pretty much on the Fellagy-Sunter algorithm, which was developed in, or methodology that was developed in 1969, I believe. It uses a series of match scores or match weights to order all the potential linkage pairs, and those match scores are based on 2 probabilities, which I'll discuss shortly. They're basically the probability of seeing an agreement in each of the linking variables, conditional on whether the link is a true match or a true non-match. It's a bit more complex. It does take a bit longer to run, particularly when you have link data sets that don't link too well. There's a lot of uncertainty in the linkages. It can incorporate frequency weights. So frequency weights basically are for example, for names, there are some names that are very, very quite rare. Like, I don't think there's too many Elazars in Australia. So once you get name and age and date of birth, say, and sex, you can pretty much find me anywhere in the country. But Gene Smith or whatever, it's probably likely to be a much more common name. So we can give more weight to the rare. So we can divide names up into the rare names and the uncommon names and the common names, and give weight. So we're basically saying a rare name counts for more. Similarly for country of birth. Yeah, most Australians are born in Australia, so it doesn't really help distinguish or discriminate quite as well as a country that doesn't have very many people who have immigrated here from. String comparators. A strength of probabilistic linking is that it has a range of different string comparators, like for comparing name and address, that allows for slight differences, slight spelling differences, the like. We tend to get around that by spending a fair bit of effort on repairing and standardizing names and addresses before we do our deterministic linkage. So, for example, we will convert Bills to Williams and Jims to James, for example, before we do a linkage. And we also do a fair bit of cleaning to take out appellations or typos in names and the like. Similarly to statuses, I'm not sure how well our probabilistic linking handles statuses. Computationally, it puts a bit more of a load on it. Okay, next slide, please, Mark. I'm just going to go into a bit more detail with these two methods. So deterministic linking basically is based on decision rules, on agreement patterns in a given set of linking variables. So the deterministic linking basically takes a subset of those linking variables as which is called a pass, and it basically then does the linkages on the series of each of those passes. And we go through, sometimes have quite a few hundred passes in a deterministic linking. So it's taking pretty much most reasonable combinations of those linking variables that we think would really benefit in getting the best possible linkages. We tend to start off with the best agreeing, the best agreements, the linkages that are definitely unique and very high quality. So for example, the first pass is probably going to ask for agreement on name and address and age and sex and the like. Most people don't move, can be found at home between two, at the same, between the two different data sets. And so we can pick up good quality agreements. And then once for further passes, we tend to relax some of those. So for example, if we can't find them in a given, at their actual address, we'll loosen it up a bit to mesh blocks, census mesh blocks, or statistical area ones or whatever to try and find them. We might also relax some of the other variables and the like. So I guess a fair question to ask is, well, how do we order those passes? And I'll get to that shortly. But uniqueness, pretty much, it becomes a fairly important requirement. And obviously in the first pass, as I just said, uniqueness is the highest. And as we get down to the last passes, we're kind of trying to pick up the stragglers, the ones that we haven't picked up before, and that tends to be less uniqueness. And the fundamental question is, where do we call it quits? Where do we stop? And the false positives tend to be least, obviously, with the first pass, and they can start to increase. And this is where, like that precision curve comes into it, where we decide to stop it. Now, uniqueness does tend to relate to precision generally, and we use uniqueness rate, which is just basically, this is a uniqueness rate of the links. So for each link that we make, we also look at like how many other links to those same records on each of the data sets was also made. So if we have a link where it was a one-to-one and there was each of those records linked to no other records on the other data set, well then that's a unique, and we just basically look at the number of unique links as divided by the total number of links, and that for that pass, and that, so the best ones get used first. The marginal uniqueness rate, which is a very similar concept, except that we exclude links already made in previous passes, is used as our stopping criteria to decide where we stop. And of course, an important piece of information that we also need is our expected overlap, which I've already mentioned. In terms of the Flagey-Sunter, the probabilistic method, linkage agreement patterns correlate to the match likelihood, and the match likelihood is probabilistically based on these two quantities M and U. So M is just basically the probability that you see an agreement given by a gamma there between two records, I and J, on the respective data sets for a linkage variable L, conditional on I and J being a true match. And U is very, very similar, except that it's conditioned on the two records being a non-match. And they go into calculating match scores or weights, and then discriminating between links and non-links. Commonly, people do clerical review to try and establish the cutoff, the difference between, where you should draw the line, particularly between the links that are very certain and the links that are not, are definitely not matches. There's that grey area in the middle. And the only other thing I wanted to mention in the slide was that, well, two things rather. First of all is that there is an equivalent. So I've based, I don't know if you probably can't see at the bottom of the slide, but the content, I guess the equivalence between deterministic and probabilistic is based on an article I read by Deutsch and Harron 2018, which argues that there is an equivalence. In other words, for every deterministic linking, linking set of decision rules, you can find a set of Fellagy-Slunter match scores that and cutoffs that will give the same results, and vice versa. Also applies as well. All right, I might move on from there. Oh, one other thing I should say is that we do have quality rankings for deterministic linking. So when we do a deterministic linking, we assign grades of quality. So the very, the links that we pick up in those first passes, where we have a very high level of uniqueness, they tend to be grade 1 quality links. And then as we go down towards the bottom, the gradings start to fall away where you have higher levels of uniqueness. Okay, next slide, please, Mark. And this is how we kind of decide our cutoff or where to stop. So this is for a particular pass. We will calculate the marginal uniqueness rates versus the number of links that we made. And just like with precision, it follows a cliff type pattern. It goes along pretty flat and then starts to drop off. And basically where it starts to drop off is where we decide to draw our cutoffs, because there are risks in accepting too many false positives. I should point out that marginal uniqueness rate is not always exactly the same as precision, but for most linkages, there is a correlation. It is something that we're currently doing research in, where we're calculating precision for our deterministic linking process, so we could actually get a better handle on that, the difference between the two, and maybe probably aim just for using precision. Next slide, please, Mark. Okay, another tool that we have, so we're still talking about methods here, is the Feasibility Calculator, and this was developed by my esteemed colleague James Chipperfield, and it's basically essentially it's used, I should point out, just for probabilistic linking at the moment. We could be doing research into there's a couple of conceptual problems in applying it to deterministic linking, but it's certainly been very useful for probabilistic linking, and given the equivalence between the two, it should be possible to adapt it. So what does a feasibility calculator is a way of calculating precision for a linkage, either a linkage that we have done or a linkage that we haven't done at all. And it's a bit like the parametric bootstrap. That all the pieces of information, the only pieces of information you need are your M's and U's and your number of matches that you either expect to get or have observed from previous linkages, similar linkages that you have done. So in this particular example, we have 3 linking variables: name, age, and address. Sorry, name, address, and sex. Name, address, and age, I should say. And in the yellow are basically the links that we make, and we basically randomly draw agreement patterns using the M's. So the M's basically tell us the probability of observing an agreement given that it's a true match. So we just randomly draw from that, and then we observe whether we reproduce an agreement or a non-agreement. And so we also use a particular rule for our cutoff, what we're going to accept as a link or not accept as a link. Here we're just going to use a very simple rule that if we get 2 ticks with 2 agreements on 2 variables, then we call it a link. If we observe less than that, then we'll call it a non-link. And similarly for the non-matches, we have our U probabilities here for each of those variables, and we just randomly draw from those probabilities. I should say that we don't need any information here on the actual values of name and address. We only care here about, so it's actually quite confidential. all we care about here is whether those two variables agree across the two candidate records being linked. Next slide. Oh, the other thing, actually, I mentioned yellow here are the links that we make. Grey are the non-links. Yep, thanks. So we just repeat that over and over again. So in the first simulation, we observed we made 3 links and we made 6 non-links. In the second simulation, we again make three links, but one of the true matches became a non-link, and one of the non-matches became a link. And similarly in simulation 3, and we just continue that over and over and over again. So the feasibility calculator is quite an important tool for us. I mean, it's almost like a Swiss Army knife. It has a high range of versatility. So, for example, it enables us to estimate precision and also recall, just with the information on the M's and U's. It enables us to set cutoffs in probabilistic linking without actually needing to do clerical review, and also it also enables us to simulate false positives and false negatives. Okay, I just realised that the time is here, so I'll need to get a bit of rush on. Next slide, please, Mark. So as I said, you can identify your false positives and false negatives, and you can even calculate precision and recall based on the simulated results. And you do that over and over again, and you can calculate an average to get expected precision or expected recall as you like. As I mentioned, recall is conditional on the number of getting the number of matches correct. Next slide, please. So in terms of the ABS person linkage spine, we have 3 main data sets: Medicare, social services, and personal income tax data. And well, these are what are known as our core data sets that form a spine. And in terms of what we want out of a spine, we want high coverage. We want the good name and address history, as well as other linking variables. We want enduring IDs. Like, for example, tax file number is a pretty good one, although we only see the encrypted form of it, because once you get one, you use that for all your subsequent interactions with the tax office. We want high quality data for each for the linkage, and low levels of missingness. And these 3 data sets pretty much give us that. Next slide, please. Medicare obviously has the largest coverage. So what we do is we first of all link Medicare to social services, and then link the tax data to those 2 data sets already linked, and we form them into clusters. So very simply here, you can have, like in red, you've got your singletons, where record only comes from one of the data sets. It didn't link to any other. We can also have in yellow records that come from multiple data sets, and in green we can have duplicates where we link 2 Medicare records together. It doesn't happen an awful lot, but it does happen from time to time, and they go together to form our spine. An important thing is the spine is just kind of like a union of all of these data sets. It's not it's actually I guess the infrastructure with which we use to link other data sets to the spine in order to bring all the content or analytical data together. So the spine actually holds only minimal information, and importantly, the record identifier that tells us which record on Medicare or social services or tax linked together. The other thing is or linking of the spine, the data sets is important, like the order that we did this in, Medicare and social services, just because we know we have a much better idea of the overlap between them. Next slide, please. Okay, so the benefits of the spine. So once we have a spine going back in time, we then can bring in any other data sets which might cover different time points themselves, and we can link those to the spine and bring in the content or analytical information from those other data sets together into an assembled data linkage product, which is then made available to users, usually almost always in the data lab environment, which is highly secure. Next slide, please. Okay, in order to help improve the quality of the spine, and it's also used in the production of the spine, we use a graph-based method, which I'm not sure I've got a lot of time to spend on, but basically, when we link multiple data sets together, links are interdependent. Once we're sure of a link between two data sets, that can actually rule out links on other data sets, and that's what this method does. So there's 3 basic rules. We accept the best link. We complete with the necessary links. We complete the triangle. It's really basically transitive closure, and then we rule out or exclude any impossible links, like where links which would lead to contradictions. So next slide, please. So in this particular example, the 30, the green now, the 30 is the best link, so we pick that. Next slide, please. And then 25, we link that. Now we've got the 2 sides of a triangle. We can then triangulate to form a necessary link. Next slide, please, Mark. And that's between the Medicare and the social services. Now that's actually, and next slide, please. And now we can rule out a whole bunch of links because they mean that we would get, additional links to other records on the same data set. I should mention that this graph-based method is applied solely in order to accept single best links. So that's something I'll talk about at the end. But we tend to look for the single best links, and this algorithm helps us do that. So next slide. Now we've got all those purples there. We can essentially now go for the next best link, which is the one flagged with a weight of 18. I should say that these are basically the match scores or similar weights for each of the links between the different records. Next slide, please. And now we can rule out a whole lot of conflicting links, or impossible links as we call them, and these are the clusters that we help form. So we still do our linkages deterministically, but the graph-based method helps us basically work out that, well, there's a couple of clusters that we should still be merging. It tends not to split existing clusters that much at all. Basically because we tend to pick off the best. Most of our links are based on quite strong links, so it doesn't tend to happen that way. It doesn't really account for a lot of changes. It's like 1 or 2% improvement in terms of the setting, the establishment of the clusters. It made, and that was more the case for the first spine, but as with the successive spines, and because our linkages are getting better, we're getting more events-based or data, more history of name and address changes. We're finding that it makes less and less a difference, but it's still there as an important backup tool to assure the quality of the spine. Next slide, please. And these are just some basic statistics from our first spine on the proportion of links accepted at each stage. And you can see that we get quite a high proportion even at the very first stage. We do a final deduplication run, and the total there, I should have changed that, but basically DCAD is the domino data set, which is actually social services, and the MCD is a Medicare client data set. So so it's basically social services to Medicare, and that gets quite a high linkage. ATO is a bit less, it's 92%, but this, I think that would have largely improved with the more recent spines. Next slide, please. So in terms of one of the things that we can do is now we've got a spine, it represents the population. We can compare it with the estimated the resident population demography counts that the ABS produces. And we have the ERPs here in blue, and we can see that that tracks fairly closely. We are doing quite a large amount of work at the moment to try and improve the scope of the spine by, for example, removing people who've passed away, and trying to better include temporary migrants into the spine, which helps improve this ERP comparison. Next slide, please. In terms of overall assessment. We think we've got a bit of the spine is pretty good. We can sort of use a lot of the diagnostics we get in our linkage processes to try and highlight the quality of our linkage, both at the link record level right up to, you know, aggregate levels of, you know, the scope and coverage of the spine and the like. Over 80% of our linkages are of the highest quality, and the rest are quite high, just not as absolutely high. The use of events-based data has really greatly improved the quality, so that we can link on more than one address. And we've also done a clerical review, just an in-house clerical review of a sample of our spine elements, shows that duplication, where spine actually contains more than one person, is extremely low. Next slide, please. I'm almost there. So current areas of research. Well, the first thing is basically to extend that graph-based method to many links, mainly in order to sort of try and improve the respective link probabilities for all the edges of the graph. And secondly, it'll be very useful to extend it so that we can link not just on the person level, but also at the family level and other levels. Sometimes you can't exactly, you have more doubt as to trying to establish a link between two individual people, but when you look at their family members, their age, sex, composition and the like, you can absolutely be sure, yeah, you are looking at the same people, the same persons. Secondly, James is doing some work on instrumental variables model for improving survey estimates when linked to administrative data sources. We're also doing work to improve or estimate precision better for our deterministic linking process, to include events-based data, which actually changes a lot of the probabilities, and that's why there's a fair bit of theoretical work that has to go into that. Also, we're also working on running probabilistic linking through our deterministic linking process, where we can use that to calculate our M's and U probabilities. Incorporating linking uncertainty into analysis of linked data, which I mentioned at the beginning, I think is really important, because it's important to be able to provide users with the right tools so that they can estimate do inference on any analysis they're doing on that linked data that correctly takes into account the uncertainty due to the linkage. In other words, so that they're not going to conclude that a model parameters are significant when they're really not, and vice versa. And also Suming and Suming Tam and Dewa Tao are doing some interesting work on linkage error correction using the iterated bootstrap, which is similar to the feasibility calculator, to estimate false positives and false negatives and adjust regression estimates for that. Next slide, please. And I very quickly just mentioned a different way of thinking of that framework, and that is basically in terms of a graph approach, where you don't throw away any linkages. You're not going for a single best linkage. You include all of the different potential linkages, which enables you to be able to take account of the variation due to the linkage uncertainty, rather than focusing on true positives or false positives and false negatives, which you don't always know for sure. You could look at the variation. So next slide, please. You can look at the variation in terms of a matrix between all the different records on two data sets, A and B, and then do analysis on that to incorporate that information into any analysis. Next slide, please, Mark. And there's some references that you can refer to. I do have others if you're really interested in the topic. I can send them to you. Next slide, please. And that's it. Does anyone have any questions?